So we're here today to talk to you all about Newtone, which is a real-time AI audio plugin for DAWs that we've been working on at Cosmo. So before we start off, though, we'll just introduce ourselves without getting any feedback. My name's Andrew, and I'm an AI application engineer at Cosmo, and the tech lead on the Newtone project. I'm also a PhD researcher at the University of Glasgow. And then, I'm co-presenting with Chris here.
Hi, everybody. I'm Chris. I'm also a PhD student at Queen Mary University of London. And I'm also a research engineer at Cosmo. I've been working on Newtone and a few other projects for them over the past few years. But I'll hand it over to Andrew.
Cheers, Chris. Just to give you an outline of the agenda for today. We don't have a ton of time, but we'll be giving you an overview of Newtone, giving you a summary of what it's all about, what the project's all about, and the tools that we've built so far. That'll be with myself, and then I'll pass you over to Chris, who's going to go into the sort of deeper elements of our SDK, which is another sort of tool that works alongside our plugin. Kind of run you through what features are involved with our SDK currently, and how you can potentially participate and be involved in the community. And then, lastly, we'll talk about and show some examples of what some people have been up to so far with Newtone, like what currently some of the involvements we've had with artists and musicians that are using the tools, and some hopes for the future as well. So let's get started then. So first of all, what is Newtone? So Newtone is essentially like a platform that's aiming to bridge the gap between the AI research community, the AI audio research community, and artists and musicians that want to harness and use the latest innovations that are happening in that space. So, we identified that at the moment it's quite a procedure to take some of these latest advancements that are happening in AI and actually use them in familiar tools for artists and musicians. So that's why we built this plugin, Newtone, which allows you to quite easily take something from a research environment done in Python and actually deploy it straight in the DAW using our wrapper and our plugin. So as I said, it's essentially bridging the gap between the AI research community and the audio creators, the artists, the musicians. It's also a community, so because we're bridging the gap between these two communities, we've kind of created our own community, which is a space for collaboration between the research community and the artists as well. So we've got our own Discord, we've got a newtone.space you can check out. It's got all our resources on there for the Newtone plugin. You can access our blogs where we talk about some of the latest innovations that are going on in this area. Access to our SDK and all these sort of things as well. So just to give you an insight into why we decided to build Newtone, it's been really exciting recently. There's been some amazing breakthroughs in the neuro audio space, doing some crazy effects going on in real time. One of which is this Tombra transfer effect, which there's a few algorithms now that have been released in recent years. One was done by the Google Magenta project a couple of years ago, and then since then, Arcam have also released this other Tombra transfer effect with Rave as well, which they have their sort of differences and nuances that make them quite identifiable as well in different ways and have their own characteristics, which is quite exciting. But to give you an idea of what Tombra transfer is, if you're unfamiliar with it, it's like this idea of potentially transforming a sound into another sound and having a model that's been trained on whatever that particular sound is. So, for example, maybe one instrument being converted to another instrument, or speech to drums or something like that. These sort of effects do that. And they're performing now in real time, which is quite impressive and wasn't the case, a handful of years ago. So, and to give you an example, so DDSP here is really good at tracking pitched information. And this, I've got an example here from violin to shakuhachi, so I'll just play that. So, and then that gets transferred to shakuhachi. Nice to go on, I think. And then also we've got the rave algorithm here. This one's going from violin to speech, which is quite interesting. So, and then that turns out to be like something like this. Weirdness, but fun. So yeah, a lot of creative possibilities with these sort of effects. So yeah, like I was saying earlier, the existing workflow for people, researchers in this space, trying to take their latest innovations, their models, and actually get it in the DAW, get it in a familiar format for musicians, and being creative with the technology is it's quite a process, and involves usually working with some Python frameworks like PyTorch, which, if you're not sure, unfamiliar with that, is a framework for training deep learning models. And yeah, they've got like a high-level Python API for doing that sort of thing. So you're in a Python environment. A lot of the research that's published stays in a Python environment. You know, Colab notebooks or code and scripts. Just they're out there, but you know they're not really in a format that's like usable for creatives. So, you know, if you've like, built your model, you then need to train it. Again, it's to train a model to a high level of fidelity can take a lot of time. You need access to GPUs and things like that. Again, Newtone has a lot of pre-trained models available, and we've also got resources for training your own models. Yeah, after you train your model, like typically you would call inference on your model, and you need to write another script, maybe in Python, to do that. And you know, maybe you import an audio file, you run it through your model, you get like an output file that's the affected file, and then eventually you can stick that in your DAW and do something with it. But yeah, I think at that point you'll be maybe uninspired and bored with all the restriction that you had to kind of go through to get there. So another point just to elaborate on is, for those who are wanting to make their own models, neural audio technology, and build a plugin around that to then start using it, that again is quite an operation, and involves a certain level of expertise. Building plugins is not an easy task. So again, we've kind of dealt with a lot of that side of it for you. So this will give you a better idea of how an artist like Big Yuki here is using Newtone as part of his like creative workflow. He's in the studio right now. He trains a model on his speech, and then actually uses synthesizers to then, as an input, to control this model, and he'll get like interesting timbre effects on the output, and that's been really useful for him in the studio. So I'll play this, and you get a better idea.
この本には2小節の音楽の断片が多数収録されています。サイコロを2個振って出た値によってこれらの断片を並べていき、一つのまとまった感じ。
What's up? Big Yuki here. And man, Newtone is the happy accident. It gives me all kind of new ideas. I can't wait to write some crazy using it. Stay tuned.
Oh shit!
So, Big Yuki having a lot of fun there. I mean, it's that process of discovery that I think is really interesting here, and and really exciting as part of this neuro audio space, and the results that you can get from just like playing about with different inputs and listening to the outputs. It's quite amazing. So, okay, now let's dive a little deeper into the plugin. So we've created this universal plugin essentially that allows you to import models that you've trained. It's also got, as you can see here on the left, the model browser, which is essentially like a catalog of pre-trained models that you can just download and just load straight in and use them. So we've got quite a lot of models on there already using different architectures, AI, audio architectures, with more to come as well. On the right here, like once you've selected a model, it will take you to the control panel where you can interface with the model. We've got some global parameters here for just your generic sort of controlling the input and output, and sort of gains and things like that in the mix. And then these A, B, C, D parameters, which looks quite ambiguous at the moment, like these are actually specific parameters for the model that you've chosen to run. I'll show you in a second. I'm just going to do a demo. But when you actually hover over these parameters, once you've selected a model, you actually get the tooltips of the actual parameter names that are specific to that model. So it's a lot more clear when you're actually engaging with it. But so yeah, I think next is the demo. So one important point: plugin at the moment is available for VST3 and Audio Unit, also as a desktop standalone for Mac. We are currently working on the Windows build for it, so that'll be coming soon. But at the moment, it's Mac OS only currently. And yeah, some of the architectures that we have available, I showed you examples of DDSP and Rave. We've got sort of temporal convolutional networks as well, doing sort of reverb effects and distortion effects. And we aim to just add a lot more. And we encourage a lot of people to participate and to explore their own models and submit them to us, and we can host them as part of our catalog as well. So now it's demo time. So hopefully this goes smoothly, as it's a live demo. But I've prepared 3 examples of different content through different models to kind of show. Let's see if we get volume first. Is that my?
It's because when you plugged in, it says it's a different interface on the new Macs.
Oh, okay. That's fine. Okay, so let's see now. Yeah, we have volume. So the first example. Let's get the GUI up. So this is what you see when you load up NewTone. The first example, if I bypass NewTone for a second, is this sort of percussive, jingly sound. It's quite interesting. So I've got that looping, and if we put that through this, so I've got equipped at the moment Japanese voice model that we trained. So again, that's available on the browser here. You can see it's highlighted here as equipped. So I'll just run this through that, and you'll see what that sounds like. So I'll turn down the dry. So these, as you can see, these parameters are coming up now as I hover over. So we've got different here. These are all quite technical based on the architecture that we're using, but they're quite fun just to explore with, to be honest. You can get all sorts of sounds by. He also adds some randomness to the model. So you start to get things like that coming through. So that's one example. The next example that I've got prepared is essentially a more kind of ethereal pad-like sound. And it's going through, we've got like a choir model. It's trained on like choir data. Let's bring up this just now. So if I slow this, yeah. So this is the input, again, just sort of drone like pad. And then if I put this through the plugin, I'll bring the dry down initially. Again, adding some randomness in here. Which adds quite nice variation here. So that's a choir example. So again, you can get quite interesting textures. I think this is quite a good example of like maybe if you want to make a sound like larger, thicker sounding, like adding something like this underneath is quite an interesting use case. So, and then the last example that I've got here is actually what was it again? It was it's a bass lead. Okay, so for this one I selected a DDSP model, which again tracks these pitch, the pitch of this quite well, and again you can layer that and create quite an interesting sound. So if I enable Newtone again. This is a shakuhachi model. It doesn't sound like a shakuhachi in this example, but it's again quite interesting sound. You can change the level of breathiness in here and of the noise. So if I bring the harmonics down, you can hear that sort of high frequency information that's there. It's quite interesting. And then you can change the pitch of that as well, which is quite useful. Add some reverb. So that's it, just on its own. And that's with the original leads. So yeah, so that was three examples, just to kind of give you an idea of the different contexts that you could potentially use Newtone in. Again, like timbre transfer works quite nice with percussive stuff. Rave models are very well suited to working with percussions and transient material. DDSP is very good at working with stuff that's maybe like a lead that's got monophonic pitch. Just to give you an overview of the plugin as well from here. Again, this is our model browser. So this is actually the latest version of Newtone, which we've yet to release. It will be released this week, in fact, so stay tuned for that. But we've got some nice updates to the GUI. You can filter models here by author. You can see my famous Clipper model, which is very basic, probably the most basic model you can do, but it was mainly for an example. But like, and then yeah, so you can filter an author, an algorithm, you know. There's a great functionality here for that. Get more information, you can go to our links here as well. And yeah, you can also, you can also from the load your own up here, import your own model, which Chris is going to run you through the process of in a second. And I think some other things just to kind of go over with the plugin. It's actually built on a web stack as well, for those who are interested in the plugin development of this. This is a browser, essentially. We decided to kind of take this route as we thought it'd be, I don't know, an interesting challenge to use web technologies and JavaScript to do the UI. So that was one kind of technical thing that we're quite proud of with this plugin. Right, so I think that's enough of the demo. Quit alive. Do not save. Okay, so yeah, okay. I'll pass you on to Chris now. He's going to go into the deeper dive on the SDK and run you through that.
Cool. Thank you, Andrew. That was fantastic. And hi, everybody. I'm Chris. I worked a lot on the SDK, and I'm super excited that there's so many of you here to listen to the stuff that we've built. So yeah, I'm really interested in how do we build these models, and we've built some tools for you to be able to create your own in Python. So as you saw Anjo demo, we have a load your own button at the top there. And basically, this is kind of what I think is the magical part of Newtone, is that it enables you to do kind of this rapid prototyping iterative cycle using Python to develop your favorite DSP algorithms, or I come from a more kind of deep learning, machine learning background. So I always wanted some tool that I can just play with. And before, you would have to write Python code, then manually export audio through the Python, save it somewhere, and then listen to it, and then rinse and repeat. It's a very non-intuitive way of working with Python models. So for me, the dream with Newtone is being able to just run my own Python code quickly and just seeing what it sounds like and be able to play with it in a creative setting. And that's something we wanted to enable for everyone, creative people who don't want to download a bunch of files from the command line and running them. So that's what the SDK is supposed to do. It lets you wrap models in Python. So we've developed an SDK. It's open source. It's on GitHub. And basically, if you want to wrap your own PyTorch model, you will import our SDK with pip. And then you just basically implement a few methods in a base class, which we need to be able to surface all the relevant information for the model. So some of those methods will be the title of your model, the author, the description, what paper it was based on, if there is one. And then a few of those methods will be technical, like what kind of sampling rate and buffer size does your model take? I'll get into this quite a bit in a second, because it's a quite interesting rabbit hole that we've ended up diving down. And then finally, all you need to do is fill in this forward function, which basically defines what you do with the audio. And that can be absolutely anything, which is kind of the magical part of working with this. The only condition is that your models need to be reasonably real time. So that means they need to run pretty quickly. But as we've seen in the last few years, there's more and more machine learning models that take advantage of kind of more efficient architectures and are able to be run quite quickly on the CPU. And that's what we see with DDSP, with Rave, and there's other models too. The other huge benefit of the SDK is that you can implement new papers pretty quickly and just write it in PyTorch, see if it works, and then use the SDK to wrap it. So the link to the SDK is here. It's on GitHub. We provide some documentation, so it includes a bunch of details of how to use it. And we also have some examples in the SDK. So Andrew's famous Clipper model, it's an absolute banger of a model. So that's probably the easiest example to get started with. A Clipper is a very simple effect, but writing one with Newtone is a few lines of code, and then you can see the example there and start tinkering with your own code in the Python file. And before you know it, you'll just be, going down rabbit holes of different ways of messing with PyTorch functions and how they translate to sound. So yeah, definitely check out the SDK on GitHub. And we also have some Colab notebooks. So these are notebooks that are set up with all the steps you need to train your own DDSP and Rave models. So those models are a bit more complicated, and not everybody is familiar with how they work, and that shouldn't be a huge barrier of entry. So we created kind of a very simple way where you can run the Colabs and then train on your own data that, for example, Big Yuki was training on his voice. And that'll generate a trained model, which Google Colab gives you GPU resources, which also lowers the barrier for people who might not have a GPU at home. So it's all free, and then you can output a trained model. You can wrap it in Newtone with one line of code, and then you can import it by clicking on the load model in the plugin. So I'm going to go through the development workflow for a model. Basically, you go to our website, and then you find the link, you get to the GitHub, and then from there you can download the SDK, and you can start building your own model and wrapping it with the SDK. So that's the first step for all the Python developers or software developers or anybody who wants to just experiment. And you can just get started with an example as well. It doesn't have to be from scratch. Then, hopefully you already have the plugin, but if you don't, you also go to the website, you download the plugin, and you can load it in usually your favorite DAW, so it works in most of the popular ones. I tend to use Ableton, but we have Reaper, People, Logic People, whatever you prefer. It is a VST3 or audio unit, and it is Mac only right now, as Andrew mentioned, but we're hoping to get Windows out. And then you load the plugin, and this is kind of the part that I find the most fun, is you will export your model with the SDK. This typically takes less than 30 seconds, unless you're running a very heavy model. But you'll export the model that you're working on. We have different modes of export. One is like a quick export, and then one does extra checks, which would be for like a final release. So if you're just prototyping, you would do the quick export. You get a .nm file, which you can then load in Newtone. And then you can immediately start playing with it in the DAW. So this is really fun because I don't need to load examples and then run them through with a script and then listen to them a few minutes later. I can just immediately get reasonably real-time performance in the DAW and be creative and then make tweaks very quickly and then export a new model. So you kind of iterate over and over until you're happy with your model. Then you'll submit it as a GitHub issue. So we have a template on GitHub for you to provide a model that you've trained with our SDK. And then we'll take a look at the GitHub issue, and we'll just check that it's running, that it works, that everything's OK. And we're really happy for anybody to submit their own model. And basically, then we will upload it to S3. So from there, the models are sent to the Newtone plugins on everyone's computer, and then they can see the models in the model browser, which Andrew was demoing earlier. And that's kind of the magic, is that your model can then be sent out to anybody using the plugin, which is a really quick way to get your model accessible to anyone who wants to play with it. And your name will be there, the title, and information about the model. And then you can look like this person. You can just be jamming out with, with new models and messing around with the latest stuff. All right, so building a universal VST is really hard. We learned that kind of the hard way. Newtone was kind of born out of a hackathon project where Andrew was wrapping the original Rave algorithm. And we figured, how hard could it be? You just input some buffers, and you get out the buffers from the model in PyTorch, and that should be everything you need to do. So for people who are wondering how we run the Python models in the DAW, PyTorch has a thing called TorchScript, which will compile your model to C++, and then that can be run in a Juice plugin. So that's basically how we do that. But yeah, building a universal VST, it sucks. It's really hard for a few reasons. One is every DAW has different sampling rates, latencies, and buffer sizes. So that's something you have to account for, is that everybody's will be different. We have to report the latency of the model to the DAW, which we don't know because it's being made by you. We didn't make the model. And we have to make sure that we don't hog the CPU and just wreck your ability to have a bunch of effects. And also we have a bunch of parameters that can be remapped. They might be different for each effect, right? So that's something we need to provide flexibility over. So this is a very hard problem, and as we got into this, we started to kind of see, oh man, this is getting more and more interesting to work on. But I think one thing that's nice is Andrew has more of a VST background, and I'm more of a Python model kind of person. So we were kind of this nice yin and yang where I would want to do crazy things that are not allowed in the VST world, and Andrew would rein me in. And we kind of found this nice balance where we're doing something that should not be done in VSTs. It goes against a lot of what VSTs are meant for. They're meant for a specific purpose with specific requirements. And we're trying to do kind of the opposite, where we can run anything, but hopefully make it as easy as possible for you. The other problem is that neural networks are typically not very flexible. So they've been trained for maybe a long time with a lot of resources. We can't expect the user to just retrain their model for every buffer size or latency, buffer size or sampling rate that you need to support in a DAW. So this is an issue because we have this neural network that needs to run, and we need to support all these different DAW settings. And the other problem is the neural network might have an input that is larger than the output, so we need to handle look-behind buffers and causality, and make sure that this network always gets what it needs so that it can run in real time and still output something that the DAW can use. So these are all things that need to be considered. And on top of that, we don't only handle the audio, we also handle the parameters, which are doing something similar. But I'll get into that in a sec. So one benefit of our SDK is that it provides a bunch of things that are done for you magically. So the goal is that you just worry about the Python and then everything else just works. So we kind of handle a bunch of stuff in the background. And if you care about these things, you can actually implement them yourself. So it does give you the flexibility to work with these things, but for most users, they don't really care. They just want it to work in a DAW, and that's kind of what we focused on. So as an example, you have a DAW where you have your sampling rate, buffer size, and channels, and the delay reporting. They can change at any time and need to be handled by the plugin. And then you have the Newtone model, which is constant. So it's a constant sampling rate and buffer size that it was trained on. We actually support multiple sampling rates and buffer sizes, because some models, they support all buffer sizes and sampling rates, and some support only a specific one. So we have to handle all those cases of any combination of buffer sizes and sampling rates. And these can be weird numbers. They don't have to be powers of 2 or anything. And then we also have different mono in or stereo out combinations. So a model can be mono-mono, it can be stereo-stereo, but some models, they take in a single stream of audio and will create a stereo set of audio. So that's also something you need to handle. And then finally, a model might have delay, which then needs to be communicated back to the DAW so that it can properly synchronize all the tracks and everything. So these two worlds kind of need to be bridged in some way. Basically, Newtone has to guarantee that the model requirements will be handled, will always be met while handling any combination of DAW settings. And that is kind of the challenge that we tried to face and kind of managed to implement. So the way we do this, and I'll go over a concrete example in a second, is for the sampling rate, we have automatic model sample rate selection. So it figures out what's the best sampling rate for that model, and then it'll do real-time resampling automatically for you. We also have automatic buffer size selection. So if your model supports different buffer sizes, we figure out the best one. And then we will resize automatically while minimizing the delay that resizing will create due to the queuing of the buffers. We do automatic mono and stereo conversions, and this is handling automatically that, if you have a mono track or stereo track in the DAW and the model has some combination, it'll do any combination of those silently and in the background. And we also handle all the delay reporting. And for example, your model might be trained on a certain sampling rate and have a certain delay, but of course that delay needs to be normalized to the sampling rate of the DAW and communicated back, and then included on top of all the queuing delay that could be introduced. So I know a lot of people, they work on very low delay models, and there exist quite a few neural models that can run on any amount of samples, so they can have theoretically 0 delay or 1 sample or whatnot. But there's also a lot of models like the timbre transfer models that do require a minimum of 2048 samples. So they do introduce delay similar to like a spectral reverb might introduce. So these are things that you need to kind of balance when you're choosing which neural models to use. And we hope that as the technology progresses, that more people start researching smaller or more efficient models that also run on smaller buffer sizes, which then can handle a smaller delay, which is more important for people doing kind of feedback loops and stuff like that. So I'm going to go over the flow of the audio just so you get an idea of what's happening. So basically, you load Newtone, and we get the initial DAW settings. So we get a sampling rate, a buffer size, and the track number of channels. And this can be anything, basically. So we have no idea. Then Newtone will select the most appropriate sampling rate or buffer size. In this case, the model only supports 1, so we do 48 kilohertz. And we'll take the 512 buffer size since it's the smaller one. It makes sense in this case. This calculation is not always trivial, and you'll see in a second why. So we then calculate the resampled buffer size. So for the 128 buffer size of the DAW, it'll resample it up to 139 samples. And this is where the tricky part comes in, is that Newtone needs to handle any weird number of buffers coming in, since the resampling can result in really weird ratios. And you just need to be able to deal with 139 samples coming in consistently with a 512 or any number on the Newtone model side. Once we figure out the internal buffer size, we figure out the minimum queuing delay, which is from trying to get enough samples collected to then run the model. And in this case, it would be 512. But this calculation also depends highly on the kind of clock arithmetic of the ratio between the two sampling rates. And then we'll resize and allocate all the internal buffers and queues. So now Newtone is ready and should ideally not be allocating any memory or anything. So then now we start processing audio. And this is going to be an example of what happens for a single buffer of audio as it comes in for Newtone. So in this example, we have a Newtone model that's input mono and output stereo. So there's some models that, for example, take in audio, they compress it, and then they find a latent space of the audio and sample two slightly different versions and then create a stereo effect. That's one cool thing that you can do with neural models. So there are these new ways of thinking about models that are not necessarily common in other more traditional audio effects. So everything in the dotted box is actually running in TorchScript. So this is Python code that's been compiled to C++. And it's running on a background thread. This is kind of how we most safely handle an inherently unsafe operation for real-time requirements, which is running this arbitrary Python code. Basically, we move the incoming buffers using a thread-safe queue to a background thread into the TorchScript realm, where we then handle all the processing. And then from there, we can do our best to get the model that's running in real time to spit out the samples, which are then sent out. But we'll go through the flow here. So first, we normalize the channels. This also saves us a bunch of computation later in the flow, since we're getting rid of one of the channels for mono. So we do that automatically. And then we'll do a resampling algorithm to get the resampled buffer. Then this resampled buffer goes into an input queue, which is implemented to be highly efficient as a circular queue. And one thing I will note is we ended up writing a lot of Python code in a C++-like way because we're avoiding memory allocations and writing it to be as performant as possible, which is very weird because when you use Python, you usually don't think about these things because it's kind of done for you and you're just trying to script and create an idea. But all this stuff was kind of written so that Newtone performs as well as possible. The benefit of writing this on the TorchScript side is that if the user who is working on some neural model needs something to change, so for example, they want to implement their own custom resampling algorithm, they can in Python. They don't have to do it in C++. So even though some of this could be done on the VST C++ side, it's beneficial for us to include it in the SDK because we want to give as much control to the user if they need it. There's people who create really interesting neural models and they have certain requirements that they want to test with. And by doing this, they can do that in the SDK and we don't need to restrict them. But for people who don't want to worry about this, it just kind of works because it compiles to C++ anyways. And the other thing to consider is when we get parameters in for a Newtone model, these need to be potentially aggregated in a certain way. And for different models, that may be different depending on what the user wants. So this also gives the user the flexibility to override our aggregate function to whatever they need. And that wouldn't be possible if we wrote this in the VST on the C++ side. So then this gets sent to the Newtone model from the input queue, which then does the forward pass and is creating an output. This output then goes to the output queue, which in this case is stereo, since the model outputs stereo, and gets added to the output queue. We then pop the out buffer, which is at the resampled rate, right, of 139, since that's what the model is operating at 48 kilohertz. We then resample that back to the 128, and then we get the output buffer. And this will be in stereo, so it still matches the input of stereo. And that's what the DAW sees, and this gets sent back to the audio thread with thread-safe queues. So that's kind of a simplified idea of what is going on and the type of problems that we had to solve. But we think it's nice that we can easily let anybody update or change how some of these things work on the Python side while still preserving kind of how the VST works on the C++ side. There's a few other things that the SDK comes with. This is more for people who build new architectures, so more on the Python deep modeling side and things that I think are really useful. So when you're dealing with a model that is streamable, so what we call it runs in real time and outputs buffers one after the other, You want to prevent these kind of wasted computations that happen with convolutions, which are a very popular technique for neural audio effects. So we implement a helper function called a cached convolution, which is basically a convolution that remembers the previous state and is really essential for these kind of real-time effects that are becoming more and more popular in the literature and in the academic field of neural audio effects, and that are then coming to more practical applications for creative people to use. So we have cached convolutions. We have temporal convolutional networks included. So these are the common building block for these fast, lightweight, low delay neural audio effects. We have these circular audio queues implemented in PyTorch that don't allocate any memory, are very fast for Python. We have look-behind buffer functionality, so if your model needs to look at a bigger context window but is still causal and still outputting a fixed amount, you can just input one number in the SDK, so you just override one function and say how much look-behind you need, and we give you that as well. So we kind of handle all these things behind the scenes because we really want the user to only focus on building a cool model and not to think about all these other problems. So if you talk to people who have built neural audio effects, they always say like, they really would love to provide it as a VST because they want people to use it and creative people to have fun with it. But building a VST, if you are a Python practitioner, is just a huge pain. And that's kind of one reason why we wanted this to be as easy as possible. The other thing we do is we have a profiler in the SDK that lets you check kind of how fast your model is running. And of course, performance is different on different people's CPUs, but it gives you an idea of how close your model is to real time and can give you also suggestions on what to do if it's not fast enough. Yeah, and like I said before, it enables rapid prototyping, compatible with most DAWs, and you can, the coolest thing I think is you can map parameters to a MIDI controller, and this lets you use your hands to really mess around with the model. And some models have like a latent space, so you can play with the model in a very physical, direct way, which is impossible previously with kind of standard deep learning methods of just testing input and output and then manually fiddling with the numbers. Having physical control with your hands is a very satisfying process and much more, I think, fun than fiddling with your command lines. That's another thing that you can do with this. And yeah, here are the links to the Colab notebooks. So we'll share the slides, and if you can't access these, you can just go to the SDK, and they're linked right at the top if you want to train your own models. Cool, I'm going to hand it back to Andrew, who's going to talk a little bit more.
Yeah, so just being mindful of time, I don't think we have too much time to show the examples, but I might just show you some, maybe Big Yuki here exploring one of the speech models here. So I'll stop there, just being mindful of time. But again, we've got all these examples on our YouTube, so you can have a look there. So just to 2 seconds. Okay? Yeah. So yeah, just to kind of quickly go over some collaboration opportunities that we currently have. That we're looking for active engagement from the community on this to help us expand our catalog from what we've got at the moment. So we've got some trained models at the moment, but we want to just constantly expand that and make that much bigger and more architectures, more types of models. Again, if the community wants to get involved and help extend our SDK, maybe give us ideas for different interfaces for exploring these models, that would all be fantastic. Just you can always reach out to us or in the community as well, in the Discord community, and get involved. So this leads me on to our surprise, which I maybe just ruined because I went to it by accident. But yeah, so we're running a competition sort of early next year. It's like a month-long competition between January and February called the Neuro Audio Plugin Competition, or NAP. but it's not sleeping. It's it's actually building neuro audio effects, building neuro audio plugins. We're doing this in collaboration with the audio programmer. So I think Josh is here at the moment. So yeah, so we'll be hosting it through the audio programmer channel and streaming live events, weekly live events to do with this contest. We will have our sponsors and researchers in the field talking about neuro audio. So our sponsors so far, we've got GPU Audio involved, who will be keen to talk about their technology and what they think the future will hold for neuro audio. We've got Juice involved and MathWorks, so our sponsors will be giving away some tasty prizes for the participants or the winners of the contest. So we've got a bit much bigger announcement to come in December with all the finer details, but this is a sort of soft announcement, I suppose. To give you an overview, yeah, it'll be a month long. It'll be, the format is to submit an AI audio plugin. You can use Newtone if you want to concentrate more on building a unique model and use Newtone to deploy it and show it off, or you can potentially build your own plugin in VST and submit something like that as well. We're going to have a great lineup of judges from the sort of, mixing engineers, plugin developers, and musicians who will be judging the plugins on their usefulness, their character, performance, versatility. So that's going to be fun to see what creations you guys make. And again, yeah, we'll be doing workshops throughout the competition as well. And then, yeah, just to finish off, these are all the people that have been actively working on Newtone. So, thanks everyone who's been involved there. And lastly, yeah, thank you. Thank you for watching and listening.
Thanks, Andrew and Chris. That was really fascinating. Has anyone got any questions? We've just got a few minutes for questions.
Yeah. It seems to me that your project is offloading the model training to the end user. Wouldn't it be nice to have perhaps a showcase of 5 or 10 models that are known to be good, and maybe you're already shipping them. But what is your take on that, where the end user becomes a developer, but also has the responsibilities that come along with that?
See, so offloading the responsibilities of like training models and what sort of data they're using and all, that sort of thing. Is that what you mean, sir?
Yeah, and data curation and everything.
So at the moment, you can, if you want to publicly make your model available through Newtone, you need to submit it to Cosmo through GitHub. So we'll be curating models. We'll probably be asking more about how you trained your model. Like, as long as a model's trained on like royalty-free samples and is maybe open source, then we'll probably welcome it. But yeah, there will be a level of sensory, like as someone like uploads a model, and then we'll probably have to investigate. So we won't just be blindly uploading sort of models to Newtone in case that comes back to bite us all. So one day in the future, but yeah.
Okay. Any other questions? I think we've got time for maybe one more, or one or two more.
Hey. Is it possible to pull out a model, to reverse that in case a model has been submitted based on or trained with data where a legal dispute started about, and then somebody said, okay, you need to pull it off? Is that possible?
Well, the model exists in a format that is just dynamically loaded into the plugin, so there will always be like the actual original model there, and then that's obviously wrapped with our SDK, so it's compatible with the plugin. So it's a kind of, we can work backwards to get the original model. Is that what you mean? To then?
the case you have a legal dispute. So I train a model and somebody approaches me, the data you've used, it's illegal, you have to pull it off. And then it's up to you to say the Amazon S3, we need to pull it off, and all our clients will lose that model again. So would that be possible? Or
I guess, so to answer your question, whether we could pull a model, so we could remove a model from S3 if it really fails to comply with something, but ideally before somebody uploads a model, we would be checking whether the audio it was trained on was open and available. One thing that's really nice is in the audio production world, there's so many kind of free open sample packs that are interesting that I think provide no shortage of data and can provide new tone models. The other thing I'd like to point out is that with a lot of these algorithms that do timbre transfer, or these neural models that are in real time, they're quite small and compressed. So they have actually a very distinctive kind of neural audio sound to them. I would say that at the point that we're at now, it's quite different from images, where an image you can't really tell from the real one, but in this case, we're actually after the unique sounds that these models can create. So I think there's both aspects to that.
Thank you. Unfortunately, I think we're going to have to wrap it up there. Thanks, guys.